Hey everybody, and welcome back to another geometry video with me, Mr. McCall. Today we're going to be expanding the triangle interior angle theorem that we discussed before to any polygon with any number of sides. Let's take a look. So we've already discussed in class before that when you have a triangle, the interior angle sum equals 180. So that is old news. But the question is, if you expand it to polygons that have more sides, how do the interior angle sums change? So let's take an example here. I'm going to draw this random quadrilateral like so. And I'm actually going to draw this diagonal right here and divide it into two triangles. So this was a quadrilateral, the whole thing. So if this is 180 and this is 180, because we already proved that, that means that the whole thing together should be 360, yeah? Awesome. So it turns out that's 360. All right. Now, what if I do the same thing, but I'm going to draw a pentagon? So 5 sides. 1, 2, 3, 4, 5. Sure. Something like that. I could split it up like this. So now I have 3 triangles, 180, 180, 180. So that adds up to 540. Now if I do a hexagon, 1, 2, 3, 4, 5, 6. Triangle, triangle, triangle. That's 4 triangles that are each 180. 180, so that is 720. And if you have spotted the pattern right now, it looks like every time that I increase the number of sides by 1, the angle sum is increasing by 180. So every side that we add appears to add 180 to the angle sum. So if we continue on, 7 sides must be 880 more is 900, 8 sides is 1080. So just like we predicted, we could draw more of these, but I think that y'all got the point. And I assume that it'll continue adding 180. But the question is, what if we wanted to jump ahead and find out what the interior angle sum of something that had like 1,000 sides is? Is there a way to skip ahead, or do we have to start from the beginning and then count up by 180 every time? Well, we're in luck. What we're going to try and do is we're going to write a function that takes the number of sides as the input and then does the interior angle sum as the output. So the number of sides, we will call it n, as we usually do. So we want to know the interior angle sum of a polygon that has n sides. And we have a few cases here that we can use to check it. So once we finish, we can say, hey, I'm not sure if this works. Let's actually plug in some numbers and see if it works. So my first instinct is that it's got to be something that increases by 180 every time it goes up by 1. So maybe something like this. So I could have f of n equals maybe like 180n. Maybe that could work. But here's the problem. If I plug in 3 here, which is the first one, if I do f of 3, that's 180 times 3, and that gives me 540, and that's too much, right? So that's not quite right. So we want it to start with just 180. And we know it has to go up by 180 every time, so we definitely need some kind of multiplying thing here. So that didn't quite work. But what if I move it back a little bit before I start? What if I did something like 180 times n minus 2? So that way, it'll start at kind of like one side, if you think about it, 180. So 180 times n minus 2 would be 180. And if we're trying it for our triangle, we do 3 minus 2. 3 minus 2 is 1, and 1 times 180 is 1. 80. So that works. If I increase n by 1, of course, every time it'll just increase this by 180. So that looks like our function. There are 2 ways that we can prove this. One of them I'm going to do in class, which is a little bit more of a complicated method. It's called a proof by induction. But the way that I'm going to do now is a little bit more of kind of an intuitive, explaining how this works kind of method. All right. So what I have over here, we're going to just call this a general polygon. The one that I drew, of course, is a hexagon, but we're just going to pretend that is a general polygon. And I'm going to draw just kind of an arbitrary point right here. And then what I'm going to do is I'm going to connect every vertex of our polygon to that random point. And the point can be anywhere in the interior. That's the beautiful part of this proof. And I just said beautiful and proof at the same time, and y'all are like, please. But I think this is a very elegant proof. One of many that you can use to prove this theorem. So again, I'm just connecting all the vertices to this arbitrary point that I put in the middle, like this. And as you can see, just like I was doing earlier, I am slicing this hexagon, or this generalized polygon actually, into a bunch of smaller triangles. Another thing you're probably wondering is like, Mr. McCall, how on earth did you know to do this? Oh, just years of experience. So there we go. And there we go. Okay. So this has now been sliced up into a bunch of different triangles. I'm going to go ahead and recolor this midpoint. Not really midpoint, this arbitrary interior point here red. Like that. So, very clear to me that these triangles are not congruent. Some of them look kind of congruent. Maybe like this one and this one are, but that's kind of unimportant. All we care about is the angle measures. So each of these is 180 total. 180, 180, 180, 180, 180, 180. Now, the only angles that we're concerned with are these interior angles of our polygon. So each of these are the angles that we want. So we want the sum of those angles to be 180 times the number of sides minus 2. Now, here's the problem. These 180s include all of these angles in here, which are not part of those exterior angles. So, slight problem. So the total angles that we've got, we have the triangles. So this is 180 times n, which is the number of sides, again, drawn as a hexagon, but just think of it as any polygon. We have one triangle for every side. But then we also have the center and conveniently, since the center here is a full rotation, we know that that set of angles adds up to 360. So if we do the total of the triangles minus the center, that should just equal the interior angles. So that leaves us with this sum of the triangles minus the center, which, with some clever rearranging, is exactly the same as that. If I distribute this 180, it's 180 times n, 180n, 180 times negative 2, minus 360. Looks good to me. Ooh, let me move my little portrait a little bit so y'all can see that better. So 180 times n minus 360. We've done it. Again, the way I'm going to prove it in class is going to be a little different, but our little formula here, if we want to complete it, just like this. So both this version, 180 with the parentheses, is the same as this one. It's just that the one on the right here has been distributed for us. That's a little bit easier to use, I guess. Depends on your preference. But there you have it. Oops. Oh my goodness. So the sum of the interior angles of any polygon is equal to 180 times the number of sides minus 2. Pretty clever. Sounds good to me. All right. Well, again, if you have any questions, you can message me on Schoology. And as always, thanks for watching, and I'll see you next time.